All right. So for the second part of 7.1, we're going to actually apply this idea of exponential growth and decay to look at some real world situations. Um, of all the different things that we study, exponential growth and decay is probably the most often, the most popular type of growth that you'll see. And we'll show you a couple examples of that in this much briefer video than the first one. So our EQ is, how can I predict future values using exponential growth and decay? So we're going to use present values to estimate or find future values. First of all, we're going to be dealing a lot with percentages today. So let's just review how to find a percentage of a number. So how do I find 50% of 35? Well, 50%, we have to first change to a decimal. So there's two ways to do this. You can either do 50 divided by 100, which will give you 0.5 or 0.50. Or some people are taught that if this is the decimal, move it twice to the left and you get 0.50. Either way, doesn't matter how you do it. Either divide by 100 or move the decimal twice to the left. So to find 50% of 35, I need to take 0.50 and multiply it by 35. Okay. If I do that in a calculator, I'm going to get 17.5, which 50% is the same as half, and 17.5 is half of 35. Okay. I like the decimal moving method, especially if my percentage has a decimal in it. So 1, 2 to the left. So 21.3% is 0.213 of 56. So 0.213 over 56 is not divided. 0.213 times 56 is 11.928. We're going to be dealing a lot with money today, so I'm going to actually round 0.928 up to 0.93. That's not exact, but it is just a rounded number. And then finally, 137% of 11. If you like the other method, I can take 137% divided by 100, and that's 1.37 times 11. So times by 11, you get 15.07. Okay. This is kind of bothering me because 11.93 is not the exact answer. It's 11.928, but whatever. Okay. All right. So percentages of numbers going to be a big deal today. Percentage change. So if you get, if there's a 30% off sale, if there's if a city's population is growing at 5% per year. Okay, these are examples of exponential growth or decay that's just not using those words. So the type of formula we're going to use for exponential growth is something that looks like this. Okay, it's A of t, which is just going to be our future value. This is just using function notation. Just like we said yesterday, the small letter a is still going to represent our present value or our start value. Okay. Now, what's in parentheses here is 1 plus r, or in the other version, it's 1 minus r. And the reason that we have that 1 plus is because we saw in the previous video, if you have a growth factor of exactly 1, you have a flat graph, which isn't interesting because it's going to be flat and never going to move. So we have to either go above 1 if we want growth, or we need to go below 1 if we want decay. And so we have this 1 plus r, which r is going to be the percent change. But the most important part is this has to be written as a decimal. Okay. If it's a 5% increase, you can't just put the number 5 in there. It has to be 0.05. Then finally, we have t, which is time. Often this is in years, but not always. Okay. So this is exponential growth because it's 1 plus. This is the exact same formula, but because of the minus sign, this is going to be decay. So you have to decide which one you're using based on what kind of situation do you have? Do you have a situation where the value is growing or where it's decaying / getting smaller? I'm not going to fill out the rest of this because I already said it as we went. So here's an example. The number of drivers under the age of 20 in Minnesota has gone down each year since 2001. In 2010, there were 280,000 drivers under the age of 20, with that number falling 2% every year. So every year there's 2% fewer drivers than there were the year before. How many drivers are there in Minnesota under 20 years old today? So here's what we're going to do. This 2001 is kind of unnecessary information. Not kind of, it is unnecessary information. Okay. Really, this whole first sentence isn't super vital other than the fact that we're being told that the numbers are going down. Okay, which tells us we'll have a decay problem. So in 2010, there were 280,000 drivers. So there's my start value. So 280,000 is going to be my start value. With that number falling 2% every year, which means I have a decay. Question is, how many drivers are there in Minnesota under 20 years old today? So if I set up A of T equals A times 1 plus R to the T. Okay. A I know is 280,000. That's my start value. I'm trying to figure out the future value, so I'm going to leave that blank for now. Then in parentheses is going to go 1 plus the percent change as a decimal. Now I've already messed up because the percentage change is actually going down 2%. So these should both be minus signs. 1 minus, 1 minus. And then since it's R, my percentage was 2%, which as a decimal is 0.02. Okay, not 0.2, not 2, but 0.02. And then this is going to be raised to the T. And this is the part where you got to think through a little bit. Our start value that we were given of 280,000 was in the year 2010. The question is, how many drivers are there in Minnesota under 20 years old today? Well, we're in the year 2020, or whatever year you're watching this video. Okay. And so currently, as I sit here right now recording this, this is 10 years later. I am currently in the year 2020, 10 years after the 280,000. So I'm going to raise to the 10th power. Okay. So what's kind of nice about this is you can go through this and do it with order of operations if you want, or you can just type the whole dang thing into your calculator at one time. So 280,000 times 1 minus 0.02 to the power of 10. So we're talking people, so I'm not going to have any decimals here. So I'm going to round my answer to the nearest whole number, and we have 228,780 is the number of what we would estimate the number of drivers under 20 years old to be. Okay, so that's how we're going to use a word problem or a real world situation and apply this formula. I live in Apple Valley. The city of Apple Valley currently has 50,000 people, and it's expected to grow by 1.5% every year. How many people will be in Apple Valley in 10 years? So, again, we have a start value of 50,000. It is growing by 1.5%. So I am going to use the plus version this time. So my future value is going to be my current value or my start value. I guess I should say start value. Times 1 plus 1.5%. You got to be careful because a lot of people will think it's 0.15, and that's a common answer, but it's 0.015. Make sure you move that decimal twice, and then again raised to the 10th power in this case because I wanted 10 years later. So this is 1 plus 0.015 raised to the 10th power. 58,027. Again, I'm talking people, so I'm going to not include that decimal at all. 58,027. Okay, so we had one exponential decay, one exponential growth. Go ahead and pause the video real quick. This is interest, so dealing with money. What happens if I invest $5,000 and it's paying 4.2% interest annually, meaning per year? Okay. All right. So $5,000 is my start value. Paying 4.2%, which means my balance is growing. So this is exponential growth. How much will his investment be worth when he retires in 30 years? Okay. Now, I don't know if I'm actually going to retire in 30 years or not, but we'll just use that. You notice I just put y equals instead of the a of t. To stay consistent, I can put that, but you can also just put y equals. 50,000 times 1 plus 4.2% is 0.042, then raised to the power of 30. So 50,000, no, 5,000 times 1 plus 0.042 raised to the 30th. Now, since we're talking money, we're going to round to the nearest cent. So it's $17,179.15, which isn't bad considering I only put $5,000 in. Not only, but if you can triple your money and then some, it's not a bad deal. Okay. Quick aside, once you get a job and you leave high school and you're done with college or whatever you do, start saving money as soon as you can. Okay, this is real life. I wish we had more time to go into it. I don't. Some banks and some payment accounts do interest, which is where they pay you money for putting money in the bank. They do what's called interest compounded monthly or compounded quarterly. And what that means is they are making you a payment every month instead of once a year, like the previous example. Okay. So if you have a monthly interest payment, means you get paid at the middle or the end of every month. That is going to happen 12 months in a year. So a monthly payment happens 12 times per year. And if you have a quarterly interest payment, okay, quarterly means they pay you every quarter of a year, which is every 3 months, but that means you get 4 payments per year. Okay, so quarterly interest payments 4 times a year. We're going to use those numbers to look at a couple more examples, and we'll wrap this up. Now, if the bank that you use or whatever investment account does compounding monthly or quarterly, we have to use a slightly different formula here. And the only difference is this introduction of the letter N. And N is simply the number of payments per year that you are getting. T is still the number of years, R is still the interest rate or the percentage change as a decimal. The only thing that we have to throw in is that divided by N. Okay. So let's look at an example real quick. P being the start value or the present value. If you're going to put $5,000, so let's just use this nice round number of $5,000, and it earns 5% interest compounded monthly. Okay. So 5% interest means I have 5%, but as a decimal, that's 0.05. Okay. N is the number of times per year you're getting paid. We're getting paid monthly. The question was, what will that be worth in 10 years? So T is going to be 10 here. So if I just use these numbers and then set up this equation right here, I'm going to see that I have A equals 5,000, 1 plus 0.05 divided by 12 to the power of 12 times 10, which is N times T. Okay. You can type all this in the calculator in one step, but if you're not careful, the exponent can get messed up a little bit. So what I recommend is that you just normally, that's a pretty simple calculation. 12 times 10 is 120. So when I type this in the calculator, I'm going to type everything the exact same, but I am going to do just to the power of 120. And that will give me my the value of my $5,000 at the end of 10 years. And the reason it's 120, not that this really matters, is it's a total of 120 payments. If you get paid every month for 10 years, that's 120 months total. So $5,000 becomes $8,235. And if we round, 5 cents. So you made 3,200 bucks just by letting your money sit there. Not bad. One more example, real quick. If I put $10,000 into an account paying 4.3%, but it's compounded quarterly, let's say I really like teaching, and so I'm going to retire in 40 years instead. So $10,000 is my P value. My interest rate is 4.3%, which is 0.043. Quarterly, so I'm getting paid 4 times a year for 40 years. I'm just going to do this right away. So N times T is 4 times 40, which means I'm going to get a total of 160 payments. Okay. So if we find my future value, the start value is $10,000. 1 plus 0.043 divided by 4, because it was quarterly, and then I had 160 payments total. So if I type that into the calculator, 1 plus 0.043. Now, the last couple examples have all been plus, but make sure, right, with money it should be adding, but sometimes don't forget that there's also decay, which is 1 minus. I did not use the exponent button, which is going to be unfortunate. 160. $55,335 and a penny. Pretty good. Again, it's 40 years, which is a ton of time, but $10,000 becoming $50,000 is pretty impressive. Okay. So, to summarize, how can I predict future values using exponential growth and decay? For growth, we have A is equal to the present value times 1 plus R to the T. And for decay, we have A of T equals P times 1 minus R to the T. And again, there's a big difference in whether it's decay or are we talking about growth. And that'll do it for 7.1.